Hey everyone, welcome to this video. We are going to talk about sequence to sequence. So, quick refresher on RNNs. Sometimes order matters. In these two senses, in the first sense, I like carrots. In the second sense, I like cookies. Each sentence contains the same set of words, just in a different order. If our model does not take order into account, performance will suffer. Order also matters for language translation. So let's use a RNN for that. Now, a naive approach might be word by word translation. Let's translate the English sense of a fun female dog into Spanish, which would be una perra divertida. I hope I pronounced that correctly. Now, the first issue is different word ordering. So in English, fun is at the start of the sentence, and Spanish, fun is at the end of the sentence. What's another less obvious issue with word by word translation? Different sentence lengths. So in English, a fun female dog is 4 words, and Spanish, a fun female dog is 3 words. Similar to how a human translator operates, we can instead try sentence by sentence translation. Sentence to sentence translation can be thought of as sequence to sequence. Okay, wall of text incoming. For sequence to sequence, turning a sequence into another sequence, we can use two RNNs, an encoder RNN and a decoder RNN. The encoder processes the input sequence, and the encoder's final hidden state, as we can see here in the diagram, is used as the decoder's initial hidden state, or you can think of as like the initial memory. The decoder uses the encoded input sequence to generate an output sequence. If these two sentences are a little bit confusing, think of it this way. Encoder processes the input sequence, in this case, a fun female dog in English. The decoder encoded input sequence used to generate an output sequence, which is a fun female dog in Spanish. Okay, more information on sequence to sequence. An input sequence generates a new output sequence that can have a different length compared to the input sequence. I want you to focus on can have a different length compared to the input sequence. Other use cases for sequence to sequence: summarization, right? You get like a long text and you summarize it down to maybe a few sentences. Answering questions, chatting, and these are the more obvious examples. However, there are issues with using RNNs for sequence to sequence. Issue 1, no parallelization. To calculate hidden state 4, we need to calculate hidden state 1, then hidden state 2, and then hidden state 3. As you can see in this diagram, right? Hidden state 1, hidden state 2, hidden state 3. Issue 2, only the encoder's final hidden state is used, as you can see right here. This compression leads to information loss. Issue 3, RNNs at risk for vanishing gradients, or put more simply, long sequences become an issue. Now, earlier in the course, we did talk about LSTMs. LSTMs alleviate vanishing gradients, but still do not get rid of vanishing gradients. So again, the three issues are no parallelization, only the encoder's final hidden state is used, and long sequences become an issue. So instead of using RNNs for sequence to sequence, what if we use something else called attention instead? Transformers use attention and are replacing RNNs for sequence to sequence, and we will learn about this later on in the course. All right, that's it for this video. Thanks for watching.